Hi everybody, welcome to Glaciation Features of Deposition. I'm going to focus on how drumlins, eskers and terminal moraines are formed and take you through exactly how to make these exam answers work for you. So first of all, what does a drumlin look like? Well, this is a drumlin. Notice the main features of this of its form. It has a steep end and it has a more shallow end. On the left side, you can see the steep end. That is called the stoss. And on the right side, you can see the more shallow tail end, and that's called the lee. And the stoss and the lee will eventually allow us to determine which direction the glacier was moving across the landscape. Essentially, this is a big pile of till, that is the rubble that is eroded and pushed along by a glacier, that has been dumped and then shaped by the ice as it has moved over it and as it has melted around it. So you're looking at a big jumble of rubble that's been shaped by the ice. Drumlins often occur in what is known as a swarm. Some teachers will use the term basket of eggs, and that's also completely appropriate. This aerial shot shows you how these would kind of occur, and you can see the drumlins littered across this landscape. Some much larger, some smaller, but again, that streamlined, broadly teardrop shape is a consistent feature of a drumlin. And that is very much to do with how the ice has shaped the till that it has deposited. So let's get to the answer. How are drumlins formed? Well, as the glacier passes over the land, something called till is deposited. Till is the broken up rock that the glacier has eroded and carried with it on its journey. Now, you need to have a little bit of caution with drumlin answer because there are different theories about how this actually happens. One theory is that as the glacier moves over the land, it moves over a very large rocky outcrop or a boulder, and that it's unable to erode that rocky outcrop away. So as it moves over it, that creates friction, and that friction causes till carried within the ice, that's rocky particles carried within the ice, to gather up around that boulder blocking the path of the glacier. Another theory is that meltwater underneath the glacier deposits till, which is then subsequently shaped by the glacier's movements. Now, you can either choose to go with one or the other of these theories, or you can demonstrate your knowledge of the fact that there are multiple theories and give a brief outline of both. Regardless, you're scoring marks in this paragraph. Most drumlins have angular and unsorted till. What this means is that the broken up rocky material that makes this feature is sharp, angular, it's not smooth and rounded, and it's not sorted, it's not deposited in neat layers, it's just a big jumble. However, in some drumlins, the till is built up in layers, and hence that's why there's some debate as to exactly how drumlins are formed. If something's built up in layers, that tends to imply that it's been built up maybe by the glacier moving over the land in a series of movements, depositing material each time, or perhaps underneath the glacier, water has been flowing, depositing layer upon layer upon layer of till. And that would make for nice layers of sorted till. Most drumlins, however, do not have this. They have angular and unsorted structures, and that seems to imply that the till, the rocky material that makes up the drumlin, has been deposited in one go. It's kind of been dumped there, over a shorter period of time, and certainly not using the power of water underneath the glacier to deposit that till in nice, evenly ordered layers. Eventually, the glacier melts and retreats, leaving the moraine exposed. A drumlin is a feature, it's a moraine feature. And moraine features are made up of a mixture of rock and sediment that we would refer to as till. Now, as the ice retreats over the landscape, it's going to act on that build-up of till. However the till got there, as the ice retreats back over the land, because glaciers are mobile all the time, sometimes advancing, sometimes retreating, it's going to act on and shape that till into a streamlined shape, as you've seen in the photographs. Also, as the ice retreats, as the glacier retreats, it will have meltwater, and the meltwater flows around the drumlin, further shaping it into a streamlined teardrop shape. The lee end, that's the long, shallow end, therefore indicates the direction the meltwater flowed, because if you imagine the ice melting and washing, all that water washing around this big pile of angular, unsorted moraine, then that water is going to streamline and shape it into a smooth teardrop shape, with the pointy end pointing in the direction that the meltwater is flowing. And finally, you can score a mark for saying that drumlins often occur in swarms. At its most basic, guys, this question actually doesn't really need to be as complicated as I've made it sound. Essentially, you just need to know that drumlins occur in swarms, that the pointy end of the drumlin indicates the direction that the meltwater was flowing as it shaped the drumlin, that as the glacier retreated, it melted, and all the melting water shaped the jumbled up pile of rock into a teardrop shape, and that the jumbled up pile of rock got there because the glacier deposited it. That's the kind of more simple version. All right, let's move on. These features here are eskers. On the left, you can see a kind of snaking shape working its way across the landscape, just one of them. Might take your eye a wee minute to pick it out. That is an esker. An esker is a riverbed, and the riverbed has been formed underneath a glacier. So focusing on the left-hand picture just for starters, that whole landscape was covered by a glacier, and as you may know, at the base of a glacier there's a lot of molten water, melted water, flowing underneath the ice. It's natural that that water would flow to one common point and form under subglacier rivers. Those rivers carry sediment. That means little particles of sand and rock. They also carry till, the larger angular rocky particles that glaciers erode and carry with them. And consequentially, they deposit, these subglacial rivers deposit that material to form a riverbed. Now, the riverbed is exposed, and we can see it today because the glacier has melted away. The right-hand picture gives you an indication of the scale that this happens on. The left-hand picture gives you a nice, neat example of what an esker looks like. But the right-hand picture shows you that, in reality, underneath the glacier, there's actually numerous streams, numerous rivers, all flowing in a really complex network. And when the glacier finally retreats, because the climate's warmed up, and exposes these subglacial river networks, you would see a whole complex system of riverbeds exposed, otherwise known as eskers. Because these eskers have been formed by water that is flowing, that means that the particles of sand and silt and grit and gravel that are carried in the water, those are going to be deposited in a very ordered way. So these will be well sorted features with layers of sedimentation building up. They won't be poorly sorted. They should show neat layers of deposition. Okay, so what would a straightforward answer to this look like? Eskers form where a surface meltwater stream on the glacier melts its way down through to the bottom of the ice. Now, that happens by forming a moulin, and you'll find that there's other videos on my website which demonstrate that. So, on the surface of the glacier, there's melted water, and it flows and eventually melts its way down to the bottom of the glacier, and doing that means that it has created a moulin, a downward a hole cut down through the ice to the bottom of the glacier. Once the meltwater hits the base of the glacier, any material that it was carrying will be dumped there, and that kind of creates a cone-shaped pile called a came. From that point, the water then flows underneath the glacier, and it continues to carry any sediment, grit, gravel, and other material such as till with it. And that can form a complex network of subglacial streams. All of that sediment and till underneath in these subglacial streams will then build up into riverbeds, and they build up in layers, which go for the smallest particles are deposited last. So the heaviest, largest particles are deposited first, and the smallest, lightest particles get deposited last because they can be transported the furthest. And when the glacier melts and retreats, a long meandering riverbed is revealed with well-sorted layers of deposition. Really quite straightforward, and if you need any further explanation, you should look at the diagram demonstrations also available on this page of the website. Okay, our final depositional feature is a terminal moraine. Now, what you're seeing in this picture is not the usual picture that you would perhaps use for a terminal moraine. Go ahead and Google terminal moraine for yourself, and you'll see hundreds of pictures. But I like this photo because it shows this glacier has the nickname the mothership, by the way, because of its shape. You can kind of see why. This shows the snout of a glacier. You are looking at the end of a glacier. It's about 3 miles wide, to give you a sense of scale. But that glacier is moving towards you, and you're looking at it end on. Now, if you look closely, you can see all along the front of the glacier there are piles, or there's one continuous pile of rubble that's being bulldozed forward. That is till, the angular broken up rock that the glacier has eroded and transported with it. And when the glacier eventually reaches its maximum extent, and begins to melt and retreat, then this line of rubble will be referred to as a terminal moraine. So just as drumlins are features of moraine and eskers are features of moraine, because they are made by the deposition of glacial till. A terminal moraine is formed by the deposition of glacial till, and as the name suggests, it's the terminal point. It's the end of the glacier's movement. So how does a terminal moraine form? Well, the first thing to mention is this bulldozing action. As the glacier moves forward, it bulldozes till at the snout of the glacier. The terminal moraine therefore marks the maximum advance of the glacier. A concept worth spending some time on in your revision is the idea that a glacier is much like a conveyor belt. So as the glacier is moving across the landscape, it's constantly scraping and eroding material underneath it and at its sides. That material is abraded and plucked and fed into the glacier ice system and moved slowly towards the front of the glacier, where it's kind of spat out at the front and adds to this bulldozing effect of material getting pushed forward. Therefore, the longer the glacier is around, for however many thousand years, the larger its terminal moraine will eventually be. If the glacier is a very short-lived glacier, it will have very little time to get for material to build up at the front. When the glacier reaches its furthest point, it melts away and it retreats, leaving the till as a terminal moraine. The till within the terminal moraine is angular and unsorted, as it's just been dumped there, just like a bulldozer would. It's not been laid down neatly by flowing water, which would deposit things in the order of heaviest first to lightest last. That's not what's happened here. The massive bulldozing power of the solid ice wall that is the glacier has just churned this stuff forward and dumped it. So it's not going to be sorted in layers, and it's all a rough jumble of angular, unrounded rocks and stones. Sometimes the terminal moraine that's formed traps melting glacier water behind it, and that forms a moraine-dammed loch. And there you have it. That's how a terminal moraine forms. Those are all three of the main depositional features that you need to know for the exam. And if you want to see practical demonstrations of how those answers would look on the page, then search for other videos on this part of the website. Thanks, everyone.